Here's an example of using cylindrical coordinates to do a triple integral. Um, this is one of the even problems out of the book. They say integrate x dv over the region E, and E is bounded by these four surfaces. When I take a look at what those surfaces are, well, z equals 0 is just the xy plane. So bounded by the xy plane. Um, x plus y plus 5 equals z. That's a plane that hits the z-axis at 5. It hits the x-axis at -5 and the y-axis at -5. So it's this plane here, right? That's the way I see it. It comes out from here over the first octant. It's up high, up in this direction. Um, anyway, then I've got the cylinder x squared plus y squared equals 4. So that's a circle. Well, if it's just in the xy plane, that's just a circle of radius 2. But since this is the z is there too, you've got the cylinder goes up from this point, right, up to there. So it's going to intersect that plane in an ellipse that goes below 5 over here and above 5 on this side. Um, Likewise, this is a cylinder of radius 3. Now you can double check that that circle on the backside doesn't hit the plane where these two planes intersect. There's a line back here, and that's on the outside of that circle, it turns out. So what I'm looking at here is this thing that's slanted at the top and flat on the bottom. So the region looks, like that. Let's see if I can dot that one instead. There we go. That's the region I'm integrating over. Okay, and I'm integrating x over that region. So, let's see what we do here. Okay, so it looks to me like the z is bounded below by that thing and above by this plane, the slanted one. And the x and y's are in this annulus down here, which, from the point of view of polar coordinates, is really nice, because that looks to me like we're going to have theta going from 0 to 2 pi and r going from 2 to 3. The z goes from 0 up to x plus y plus 5, but if I'm going to do this in cylindrical coordinates, I've got to convert that. So x is r cos theta, y is r sine theta plus 5. And then the integrand, I'm integrating x. Well, x is equal to r times cosine theta. And then I said r times cosine theta, didn't I? It's r times cosine theta. And then I have r dr d theta dz, or rx, I guess dz is on the inside. So the r and the r are going to get together to be an r squared. And then I have dz dr d theta. Okay. So there is the integral in cylindrical coordinates. Not too hard to integrate, just because there's just a z. You're going to have this top one minus that one. And then you've got a rectangular region. Well, I'm just going to worry. No, let's do it. Let's do it. So I've got 0 to 2 pi, 2 to 3. This is going to be a z. So I've got the r squared cos theta, and then times r cos theta plus r sine theta plus 5 minus what you get when you plug a 0 in, which is going to be 0. So there we go, dr d theta. So I integrated that to get z, plugged in the top, plugged in the bottom, subtract, right? If I look at this, I was thinking, oh, I'm going to be able to factor out an r, and then I have just a function of theta. I can't do that. However, I can do this. If I do the integral from 0 to 2 pi, the integral from 2 to 3, multiply it through, I guess. So I've got r cubed cosine squared theta plus r cubed sine theta cos theta, and then plus a 5r squared cos theta dr d theta. So what I would do is I would split this into two integrals, this one and that one, and then add the results together. Because this one you can factor out an r cubed, and you'd have an r cubed times just a function of theta. Likewise, on this one, you have an r squared times a function just of theta. Since this is a rectangular region, that's nice to be able to split them up. You can't just split them up right away because this doesn't factor well enough. The r squared and the r cubes would leave an r inside. So break it into two integrals and then do them separately. And I'm going to leave that for you to do.